plan is to talk a little bit about the workshop and then have final presentations from the challenge areas that have been working on these projects for the last month and a half, roughly. And so we're going to start with the vision project, then grill, then learning to raise, then metal. But before we go into those challenges, we're going to tell you a little bit about the workshop in hindsight. And so the agenda today is to give you a workshop summary and then to go through these challenge projects in the order I just told you about. And then to remind you about the Misha Prize and to say thank you and goodbye and actually welcome you to an after party in a gather town that Terry Stewart has set up. So the workshop in a nutshell, we had over 1,000 registered participants from all career stages in all parts of the world. And you can see here some statistics of that is roughly, well, you know, half undergraduates, I guess, male, maybe half another 20% female, it's a bunch of PhDs, some professors. If you look at the type of organizations, it's mostly academic, but substantial industrial and government lab. You look at the current positions, you know, about half were actually undergraduate students, had this many postdocs, this many faculty here, this many tactical staff from companies, and 10% of other stuff, not clear exactly what. But they were from all regions of the world here. These kind of represent the US, the bulk, but there's also Europe and Asia, basically geographically spread in a quite uniform way all across the world. And we had over 500 people out of the 1,000. We got 500 people into the Slack workspace, and during the entire workshop, there were over 9,000 messages sent in Slack. So it's pretty active, especially in the challenge areas. You can see here people passing data around. And we collected some more than 30 videos of talks and different events in our YouTube unlisted video channel that you all have access to through Slack. We're going to clean that up and try to make the best talks publicly released after the workshop. So that's all I want to say about this, and just move on to the 4 challenge projects, which were organized by roughly about 8 people, but gathered in the end about 30 quite active participants. And that's quite similar to the usual summer workshop where we have the 30 invited students and postdocs that work on projects. So now I think we're just going to go straight on to that and to the first one, which is Cornelia Vermeuler's vision challenge, right? Which is insights into the early motion pathway.
Okay.
So Cornelia,
yes,
you take over the screen.
Pathway, and the participants were from Maryland, from China, and from Singapore, University of Singapore, and from Canada, Francisco. Here are the names. So to remind you, we set out with the challenge of explaining motion illusions, and the final goal, which is still ongoing, is that any of a number of motion illusions can be put into our programs that we're going to create, and a kind of explanation comes out. And these motion illusions that we set out to tackle correspond to 5 concepts that we also have been intuitively understanding earlier or written classical things. So the first one being that there is statistical bias, which I'm going to say immediately. One gives image motion, and that creates illusions like the one on your right called ouchie. And that should be a universal principle. Another one, if we model the human motion system, which really has to be causal, meaning predictive. So you use filters that are much faster, then you will also get illusions like the snake illusion. And we basically achieved this. That's what our talks are going to be about. We have neural network simulations for this. Going on, then we want to also, don't have the segmentation yet, that's still going work in progress, but the motion is explained. Then we also want to go on with illusions like this, Levian, that involves 3D motion and event-based, which is also actually going on, but that's not what we're talking about. So to just explain what will be coming now as a neural network explanation, why is there bias? Because when we compute image motion, these are these little vectors that tell us how an image point moves from frame to frame. This is really a two-stage process. Usually the first stage, if we look very locally, we only can get the so-called gradient motion or normal flow. And then we need to impose somehow, assume that in a neighborhood, it's similar, it's smooth, it's constant. So when we do this in some way, high level, we do an estimation problem, which means graphically we intersect the normal flow vectors. So each of these little vectors, each of the constraints will give us one such constraint. We only can say the flow is going to be on a line. And we need multiple in order to intersect these lines to get the flow. But if there's noise, they're not going to intersect. And then we pull out our tools and do the best we can, what is called estimation theory. And we have shown if you do LS, least squares estimation, you're going to get something like bias, which means if you did it 1,000,000 times, in average, it's not gonna be correct. It has a bias, it's gonna be underestimated. So, and why mathematically we can write this thing, what I just told you, smoothness constraint as a simple equation that everybody knows, AX is B. And if there's noise also in A, we can show there's bias. That's the idea. But the equation is AXB that you will see coming up. And then we also have a second illusion that we tackled, as mentioned, which is when we really model how the vision system does things, it's computing its derivatives in space in a symmetric way, here showing with a Gabor filter. But when we go in time, we cannot use a Gabor filter. Otherwise, we would be half a filter behind. So what engineers do, they usually use as an envelope a filter that is weight much more in the present and less in the past. That's called a causal filter. So it estimates the thing much closer to the end in order to predict. And such filters can be shown on these specific signals at certain scale that are gonna be wrong. Okay, and now I will pass on to Yuan Song, who will explain our work on the bias. And I just share to all participants. Is that work? And finish my sharing.
You want him to share the screen, or are you going to present the
Yes, I
slide?
want him to share the screen and go to the slides.
Okay, so you should take over the screen sharing. Thanks.
Yes, stop share.
Okay. Let me share my screen. Can you hear? Can you see my screen?
Yes.
Yeah, very good.
Yeah. Okay. So thanks for the prof's introduction. I will report some results on the illusion perception by the deep neural network. So we actually train a neural network to estimate optic flow from the two consecutive frames. That means we input 2 frames. These 2 frames have some, you can see some object movement. And this neural network will give you the estimated flow. Okay, so this flow means optical flow. That means assume that there is an object with the coordinate x, y. They will translate to x plus u, y plus v. U and v are the shift vector, like this shift. And the basic assumption of the optical flow is brightness consistent constraint. That means when the object moving, its appearance does not change. Okay, everything comes from this equation. Okay, so we train this neural network by unsupervised learning. Unsupervised learning meaning we train the neural network without refer to the ground truth flow. Okay, so the cost function here, we use n 2-frame samples and the cost function like this way. This is so-called photometric loss, meaning that given the frame 1, you're warping by this flow and make them closeness. Okay, so this is the photometric loss. This is the regularizer. The gradient of this psi asks the predict flow becomes smooth. Okay, we use this unsupervised learning, and our training sets. We have 2 training sets. The first one is the BSDS 500. You can see that mostly they do the translation. This is for test Ultra pattern. And another one is the chair SD home. You can find that some object that can moving. We use these 2 training sets. Okay, so after the neural network is trained, we want to see the prediction for these 2 specific patterns. The one is the Ultra illusion. Another one is the wheel illusion. Okay, let's look at the first one, the Ultra illusion. So for the Ultra pattern, the ground truth flow is, you can find the ground truth flow is moving diagonally. But your observation is there are 2 different segments. The inner part and the outer part are moving in different directions. We actually want our neural network to check if they can get the same result as our eyes. Okay, so this is the result for, this is one result. You can find that I synthesize this Ultra pattern by moving diagonally downwards. Okay, and this is a ground truth flow for all of this pattern. But if I use the trained neural network to test this pattern, this 2 frame, you get this kind of thing. The inner part and the outer part are moving in different directions. You can view by this arrow plot, or you can view by this color plot. This color plot means the color is a direction. This yellow is go downwards, and this orange go to that direction. Okay. So this is the one test. Another test is we moving horizontally that direction, and this is ground truth. But if you put it into a neural network, it estimates like this one. The inner part goes that direction, but the outer part is go upward, downwards. Okay, there are more results like this one. I synthesized by the moving of diagonally upper like this one, but the result is the inner part goes that one, but the outer part goes upwards. So that means for the Ultra pattern, if you use a training neural network to test, it will give you the wrong estimation as our perception. Okay. Another test is on the wheel illusion. Wheel illusion is observed when you're moving away or towards to the pattern. I make this animation to synthesize what is moving away, what is moving towards to this pattern. You can find that when moving away, that means zoom out. The outer ring rotate anti-clockwise, and the inner ring rotate clockwise. And when you're moving towards, the outer ring rotate clockwise, and the inner ring rotate anti-clockwise. Okay, so this is our perception. So what about neural network? So this is the result from neural network. This is the wheel pattern, and I'm moving away means it's the radius shrinkage, like this one. And this ground truth flow, this is the predict flow. This animation shows the difference. You can find that predict flow actually moving up in the outer ring, it goes that direction, and the inner ring goes that direction. It's actually similar to our perception. Okay, I also draw some arrow plots. This is the ground truth. Because you're moving away, the ground truth flow should be go to the inward, but this is a prediction. This outer circle goes this one, inner circle goes this one. Okay, so also for the bias plot means what? that we use the estimated flow minus ground truth flow to see what direction we will give. You can find that the outer circle mostly for the anti-clockwise, and the inner circle mostly give you the clockwise, just as our perception. Okay, I do another test. When you, this is for the moving towards. Moving towards means the radius become larger. This will become larger. And this ground truth flow, this is a predicted flow, and this is a difference. You can find that this yellow goes that direction, and this blue goes this direction. So the outer circle go clockwise, and the inner circle go anti-clockwise. Okay. So this is also the arrow plot for this case. In this case, for the outer circle, they go clockwise, and the inner circle you can find they go the anti-clockwise. Okay, and also the arrow plot, outer circle clockwise and the inner circle anti-clockwise. Okay, so these two experiments show that the neural net prediction for these two optical illusion is similar to our perception. Okay. Then I have more discussion. So this is the loss function I used. So this is the photometric loss. This is the smooth term. So we want to examine both terms. For this term, we want to check the large smooth parameter versus small smooth parameter. When the smooth parameter is large, like lambda equal to 1, you can expect the predict flow is smooth. So the boundary here is a little bit blurry compared with the small lambda, small regularization parameter. Okay. Another discussion is on the this fidelity term of photometric loss. We try the L1, so the P equal to 1, and the L2 squared, so P equal to 2. This is the result for the L1 fidelity term, and this is the result for the L2 fidelity term. This is a ground truth flow. You can find that if we use both L1 and L2 fidelity term, both give you the biased flow estimation. You can find the inner part and the outer part are different. But visually, the bias on L2 is more severe than L1. Okay. And another thing is we want to compare with the neural network prediction versus some least squared estimator, like the Lucas-Canard algorithm. So this is the neural network prediction. This is the one case. This is another case, and you can find that both estimator has the same bias behavior. The inner part is quite similar, but the neural network give you a relatively larger bias compared with a simple least square. Okay. So the neural network estimator, as this plot shows that it's related to the least squared estimator. Okay, so we actually want to check if they have the same quantitative results. So that means we have already know that for the least squared estimator, its conditional number that A is equal to B, that conditional number of A characterize the bias. Okay, then we want to check if the neural network give you that number also characterize the neural network's prediction. So we use the textual images. So you can find that there are 4 textual images, and I synthesize some motion. This is just a translation. There are 4 angles, and this is the estimated flow. You can find that for the small condition number, the estimate flow is relatively good. But if the condition number is large, most part has some bias. So that means it shows that the neural network gives a similar behavior like the least square estimator. Okay, that's all for my part.
Okay, thank you, Yoae-sung. So let me summarize. So what we found is that basically, however we set the network up, as long as it minimizes photometric loss, whether with L1 norm or L2 norm, the bias is there. It seems to be a very general principle and proof to follow. Okay, so
There's a question, Cornelia, from the audience, or
what's
more
the
strictly.
effect of the bias? I mean, usually in general situation, we have worse problems because of coming from the discontinuities, but knowing about the bias can help you certain things. For example, if you have applications like estimating the corners of a mouse in facial recognition. These are situations where there's really very large conditioning number, nearly 2 parallel edges. So in such cases, if you know about it, and you could actually even correct, right? Because we kind of know what the form of the bias is. But in this case, we wanted to really look into, I mean, before we talked about standard L2, now neural network is highly nonlinear functions, and we still get the same. So I think
there's another question, Cornelia, from Simone Miller, cleave to everyone. Did you see it there? For computing the movement.
So this illusion should be really experienced is much stronger, first of all, if you move your head, not your thing. So we assume in and out. So we assume that usually the outer thing is assumed as the main motion, that's the peripheral motion. And then the inner one has a different one, which is then seen as independent movement. So that is the interpretation. So, and that's actually how it is really in biological motion. We use the periphery to a large degree for our own ego motion, right? And then what is residual is seen as independent. Yeah, okay. So we're moving on with the next talk, which is given by Levi and Chetan.
Hi. Am I able to share my screen? Let me try. I can. Can you see that?
Yeah.
All right. So we're running a little low on time, but we'll be quick. So our question was, can neural networks see the snake illusion? So the snake illusion is here on the screen. Hopefully when you look at the middle, you should see that the edges of your periphery vision, the wheels are rotating. And this is actually due to the saccadic eye movements, we believe. So your eyes move slightly, your brain estimates the motion, and then it subtracts out your eye motion, but there's an error, which elicits the rotational flow. And the bio-inspired explanation, Dr. Mueller kind of went over this a little bit, but the idea is the causal filtering to get an instantaneous motion estimate in the time area creates this bias when presented with the anti-symmetric patterns, as in the snake illusion and the Donguri pattern. So if you look at this next slide, this is the result of the convolution. So when we take this time filter here, and we convolve it with a slice of the Donguri pattern here, for lower pass frequencies, we get nice smoothing. And for higher ones, we get 2 spikes. But when we have a critical frequency, in this case omega equals 1, we kind of get a blending of the 2 spikes. And when you do the classical flow estimation with this type of filtering, this is when you start to get the bias, when the temporal filter has this kind of blurring of 2 edges, but still with a divot in the middle. And so when we try to connect that with a neural network, we need to find a way to train the network so that it exhibits similar effects, so that hopefully it develops similar filtering properties. And so we did that in two ways. The one way was to weight pass flow error less. So if a network outputs multiple flow estimates for multiple time instances, we should tell it that the most temporally instantaneous flow is more important. And to do that, we also had to extend our networks to be multi-frame. So Chetan will talk about that a little bit.
Hi, I'm Chetan. Am I audible?
Yes.
Yeah, so to implement this causality, we modified our popular FlowNet variant, the FlowNet to ST. So the FlowNet ST is designed for like small displacement, so like illusion motions and also saccadic movements. So what we do is we train our network with a small displacement data set this is a variant of flying chase on the central data set, which was rendered at 1000 frames per second. And we've experiment with different loss functions such as unsupervised, supervised, and warp to future. So we tried a bunch of things. As you can see, like we tried like and as later Levi explains like what all things we tried, which works, which doesn't work. Next frame. So the one major difference when compared to the other flow network is we had the multi-frame extension. So we add this by like concatenating the input frames with depth-wise, and we feed the input frames to network, and we predict the multiple frame flow outputs. You can see the n frames, the n can go from 2 to 4, and the m, which is the number of flow outputs, can go from 1 flow output to like 3 flow outputs. So to enforce the causality, so what we do is we weigh the flow error asymmetrically. So the idea here is the latest or the recent flow error will get a higher weight than the past flow error. As you can see, asymmetric weights here, like we are given like a 1, 2, and 3. The W3 is a recent flow error, and the W1 is a past flow error. So we also compare with the symmetric weights and asymmetric weights, and we can show like we show that how the results are different. Next slide. So as we know, illusions are perceived with the small like saccadic movements of the eye. We need to like simulate that environment. So what we do is we transform the illusion pattern with the like a roll pitch drawn from a normal distribution of 0 to 0.2. And we test our network with the snake and dongri pattern. So it works for the snake pattern, and we still trying with the dongri. It's also the one here is the scale and the resolution is also very important. So that's why we still haven't got results with dongri, but we have results for snake.
All right, so now we're going to present some of our results. So the first thing we did was establish some negative results for when we expect no illusory flow to be detected. And so on the left, we have the results from a standard optical flow network that takes in 2 frames and estimates 1 flow between those 2 frames. Of course, the weighting in that case is just 1 because there's only 1 frame, 1 flow frame to estimate the error with. So we have our predicted flow on the left, our ground truth flow for warping the snake pattern, and then we plot on the right the angle of the error. So we take the prediction minus the ground truth, we get the residual, and then we plot the angle of that here with the arrows. And what we're looking for is some swirls around the areas of the snake. So if we blow that up, we can see that there's really no swirling, which is as expected. None of our new constraints that we hope to elicit causal effects are here yet. So we do that again with a 3 frame and 2 flow out extension, and symmetric weighting again, 1, 1. And again, no real swirling. There's something funny going on down here, but we found that wasn't consistent between different motions. So we can't say that is what we're looking for. Plus, it's not what we're looking for. We don't want that to happen with symmetric weights. And again, when we do 3 frame in, 3 flow out, again, we don't have any swirls. So now what gets interesting is when we go to the anti-symmetric weighting. So we do a 1-2 weighting. And so immediately we can see that the predicted flow has something funny going on. And when we subtract it out and then plot the angle, we see distinct swirling. So let me pull this up. So up here is where one of the snake patterns would be. And we see a counterclockwise rotation, which is as humans perceive it. And then on the right, we have the clockwise rotation, which is also as people perceive it because the snake pattern reverses direction in this region of the image. and so on through the image. It just keeps reversing. Now, when we do this with the 3 frames in and 3 flows out, we get the same effects. Again, we have anti-symmetric weighting again. Now it's just 1, 2, 3, extend 1 more frame. And again, we have the same kind of swirling. It's slightly different, but it's qualitatively the same. Okay. So with our conclusions, we found that the classic 2-frame, 1 flow output networks don't see the illusory rotation, which was as expected. But to get the network to better approximate a causal filter, so a more instantaneous estimate of flow, we were able to get illusory rotation in that situation. So the way we did that was with a 3-frame input, 2 to 3 flows output, and some bias weighting in time. And that bias weighting seems to be the effect that caused the illusory rotation to be seen. Now, the biological motivation, as we discussed, could be better prediction. More instantaneous estimates of derivatives are useful for more useful prediction. Not, a biological system doesn't want to wait for one frame to get an estimate. It wants it now. And then also I wanted to note that we did, we trained 26 different networks with different loss functions, but we found that the supervised training with the bias weighting, which is really the simplest way to train things, was enough to elicit the illusory rotation and really gave the best contrast. So, and with that, we can take questions.
Nice. I put a question there, which was, the first one was about the weighting, this 1-2 weighting, but that was already nicely answered by Chetan. I had another question was, what sets that lovely spatial scale of these rotary spiral patterns that you see? What sets that scale in your?
Yeah. So here, these first 2 plots, these are the flow vectors, but they're scaled up by 15 times. So, in the middle, we have less motion, and in the end, we have more. But then here, I actually plotted all the vectors at the same magnitude, the same length, so we could clearly see just the angular error. Because without that, the vectors are very small, and it's hard to see.
No, but I'm asking what sets the scale of that pattern in the scene?
Okay, so the illusion only happens at certain scale, because intuitively you really need filters that kind of span these black bars or white bars, right? So
sorry, it's the input pattern itself that sets it because it's being driven by it.
Right. We use the wheel illusion because it has the pattern at all kinds of scale, right? It's really, so we get it with some simulation. When you go to other patterns, you have to find the right scale. Mm-hmm. So that's why it's a bit easier to start with this. Mm-hmm.
Bravo.
Okay, so I think, good. This is our success story.
Yay. Yeah, so as sort of normal with Telluride work groups that I'm a part of, there tends to be lots of little projects. So I think we're going to have a lot of smaller things in different directions as part of this presentation. So we'll make all that work. The general way I'm going to organize it is I'll keep sharing the slides. But then when we get the slides that other people focused on, I'll get them to describe what happened. So everyone, be prepared that suddenly your slide will appear and you'll be expected to say something. So the overall topic, you said, was guided reinforcement and imitation learning. I think the overall topic covered the things that are going to be covered in this presentation ended up being a lot broader than that. But we'll see how that goes. I want to start with things that are going to be a little bit more reinforcement learning focused at the beginning, and then we'll go elsewhere for the others. But of course, the first step into that is not going to look like it's reinforcement learning related. This was something where one of the talk that I gave was about the talk that I gave during the initial week of Telluride was about the spatial semantic pointers, this weird way of representing time and space. And as we were playing around with reinforcement learning, it ended up being really clear that, as is sort of standard with neural networks, sparse representation ends up being a kind of an important thing when doing learning. And we ended up finding that the spatial semantic pointers ended up giving a really interesting way of making sparse neural network representations. What do I mean by that? If you have on the left is sort of the normal neural network approach, where you have a group of hidden neurons, you feed in some inputs to them, and then each neuron responds differently to those inputs. And if you have one-dimensional input, you tend to get tuning curves like what I've shown in the top left here. If you have two-dimensional inputs, you tend to get tuning curves that look kind of like what I'm showing in the bottom left. Neither of those look particularly brain-like or particularly sparse, but it turns out that if you just take your data, and even if it's not spatial data, even if it's just normal numerical data you would shove into a network, if you use that spatial semantic pointer representation, then all of a sudden you get these really nice localized response curves in your hidden layer neurons, and that seems to make it, as I'll show, is sort of might be useful for online learning. I will also point out that it's somewhat flexible in that you can also get weird tuning curves. So like it also turns out you can also get neurons. So here's like neurons that respond to two different points in the input space. So sorry, just to sort of explain what these graphs are. Each of these squares is a different neuron. And I've got two different inputs that might be going on. And so I'm just plotting the two inputs on the X and Y axis, and then the shading is just how much that neuron responds to that input. All right, so these are the sorts of tuning curves I was expecting here in the middle, where like, okay, this neuron responds to values in this range, but nothing else. But it also turns out you can just as easily have neurons that respond to two different values in the range. So no idea whether that will be useful, but it ends up being, I think, important if you're using these NEF style approaches where you're sort of designing what you want the neurons to do rather than relying on something like backprop to just sort of try to optimize what the neurons are doing. If you're actually designing things yourself, then I think these are the sorts of things you need to be aware of. As an example of why that ended up being useful and why we went in that direction, we were working with some various reinforcement learning tasks. One of the standard benchmark reinforcement learning tasks is the cart pole example, where there's a pole on a cart and you're moving a cart back and forth and you need to keep the pole balanced straight up. And on the top is what we were getting with sort of just standard neural network approaches. It was and what we're showing here is, so this is on the top left, that's the first 400 trials, then the next 400 trials, the next 400 trials, and the next 400 trials. And what we're plotting is, so with the cart pole example, you're getting a reward when the pole is pointing up, but then when the pole falls over, you get 0 reward. And so I've got multiple trials overlaid on top of each other here. The point at time when the pole falls over is the blue line in the middle. And then what these lines is the neural network's estimate for how good the current state is. So it's just sort of one of the standard components of most most reinforcement learning algorithms. And I'm plotting all of the 400 different trials that it did, what it thought the estimate of the current state is. And you can see that over time it starts getting better. You know, after 1,600 trials, it's gotten pretty good at noticing that, hey, during these points in time where the pole hasn't quite fallen over yet, but it's about to, it's starting to drop its estimate of how good the current state is. Right? So that's sort of an indication that, yes, the network is learning. But there was some weirdness. So one thing that we were sort of noting here is, look, it's taken it 1,600 trials to learn this. That's horrible. And this line that drops down, it starts going negative. And that's a little bit weird because the value of a current state is supposed to be the sum of the reward right now plus the rewards into the future. And the rewards are always positive or 0 or positive in this task. They're never negative rewards. So there is no way this thing should ever be estimating a negative reward. Like it's just wrong. And it's taking forever. And so one of the things that we were thinking was happening here is that it's because of the fact that the neurons were not very sparse in terms of the representation. So we're getting a sort of classic catastrophic forgetting problem, that changing what the neuron is, what the network is learning about one point in space is changing what it thinks about other points in space. And the standard way to get rid of that is to go with a more sparse representation. And so that's what we did. We dropped in the system that I just showed on the previous slide. And all of a sudden it now learns the task in 8 trials. Like we're down to 8 trials here, and it's now got a perfectly good estimate, doesn't go negative, figures out exactly what these things are happening. So that feels like ridiculously good to me. So that was kind of an interesting surprise. I think there's going to be a lot more that I want to explore about that, because there are some interesting parameters about, you know, how exactly do you make these things sparse with the spatial spanning point of representation. But that was a cool sort of initial result that I'm quite happy with. So that's one aspect with the cart pole sort of example. However, that was mostly focused just on, are you good at recognizing the value of the current state? We did also extend that to, okay, you know, like, how well does this actually do at doing the task of balancing the pole? And certainly we only got sort of success at balancing the pole reasonably well when using the sparse representation. Okay, let me take a step back here. So the reinforcement learning algorithm that we were playing with and implementing is a variant of the sort of the actor-critic reinforcement learning, with the particular constraints that all of the learning is online. There's no memorizing your current states, your previous states. There's no batch processing. So a lot of the tricks that are standard in reinforcement learning are not being used here. We're also restricting ourselves to entirely being a local learning rule. So it's just delta rule. There's no backprop going on here. The intent there is that this should be a rule that is implementable in neuromorphic hardware. And indeed, that's the sort of learning rule that we've put in neuromorphic hardware before. It does, the stuff we were playing with, it does work with either spiking or non-spiking. So that's not a restriction, but it does seem to require this sparse representation, and that I was not able to get good success for situations where we weren't going over to the sparse representation. But that said, it's still not a complete solution to this, even this cart pole example. So for instance, we can see here on the right, here's the sort of network behavior. So I've got 3 rows here. It's network behavior at the beginning of learning the task, middle of learning the task, and near the end of learning the task. And what I'm plotting, the top line here is the output from the network, the sort of, you know, what's the probability you should push to the left? What's the probability you should push to the right? The second row here is sort of showing, well, what's happening right now? Because this is a task where the pole falls over, you then have to reset the pole and put it back up and then let it start the task again. When these 2 lines are high, that's when I'm forcing the pole back straight up again. During this window in time, so yeah, when these 2 lines are high, that's when I'm resetting the pole. When the 2 lines are low, that's when the pole has fallen over and you're punishing the network, saying, no, that was bad. And then this spot in the middle where one line is high and the other line is low, that's when it's actually doing the task. And initially it's just behaving randomly. And so you can sort of see that it doesn't, you know, sometimes the pole just immediately falls over, sometimes it stays up for a little while, but it's just behaving randomly. As you get into the middle, as it's learning, now, okay, it's holding the pole up for longer. And then at the end, you're seeing it's holding the pole up for much longer. And you can see it sort of pushing the cart back and forth pretty regularly, and that seems to be working. So that looks great. It looks like it's definitely, and it has definitely learned something. It's not considered a technically complete solution to the task, though, because when you go ahead and look bottom graph, which is each of these points in the graph is a different trial, and I'm plotting how long it holds the pole up. Then you'll notice that, yeah, it does sometimes hit the full, yeah, so the success criteria on this task is supposed to be, can you hold the pole up for 200 time steps? And yes, it can reach that. However, it does not reach that for long. And after doing that, it has these periods of like completely forgetting what it's doing. So it'll do well on the task, and then it'll just sort of, I give up, I want to go try some other things. So that still needs to be explored about why in the world that is happening. So that's the sort of state of these sorts of things. All right, so that's enough for the simple cart pole. We wanted to get on to the Pong game, because that was one of the examples that was brought up in the Wolfgang Moss paper, because they'd done that on their reservoir system. So we also sort of pushed into that direction. Vivek, do you want to describe what happened here?
Thanks, Terry. We basically first had to explore the representation for the spatial semantic pointers, for which you can see the parameter analysis where we explored the dimensions and the scaling and what was the effect of it in terms of how the image was being represented. And once we got an optimized value, that is d equal to 1024 and scale 0.4, then we used it for the Pong example.
Yep. And so basically it's a very similar learning system. And how are you feeling about the results there?
Yeah, so basically the difference with respect to the standard networks is that the LMU is using the difference part rather than pushing it in the normal convolutional sense. And currently it's starting to learn. It seems like it will require a lot more time to learn. We have so far run examples for 10 hours or so, and still you can see the reward rate is around 0.03% so far. I've just got the GPU accelerated version of it kicked off properly now, so maybe in some time it will become more stable.
Perfect. Yep. Yeah, we sort of got into this and then noticed that in the original Wolfgang Moss paper, where they were doing the Pong game with a neural network, if you look really closely at the one of the figures in there, it points out that it required 100 million trials, and we hadn't quite realized we'd need to run things that long. So so hopefully hopefully that work. We'll continue that work, and hopefully it'll also work well. Cool, thank you. Now, since we've got Vivek on the line as well, I want to sort of start moving this in sort of fairly different directions. Do you want to also talk about this motor imagery?
Yes, so here the motivation was that we try to see how we can implement the whole normal CNN, which is used for the motor imagery tasks right now, and port it onto a spiking neural network, which is even compatible to a platform, an energy optimized platform like Lohi. So we use the network architecture, which is shown here, which is derived from the scientific reports paper. You can follow the link below for. The task has 4 class outputs and multiple subjects. And
what's the input?
So the input is a time snapshot acquired using the MNE tool, which will have the time axis and the channel axis. You can see that in the last, the layer below, the bottommost layer in the network, that shows how the input will look like.
So and so the situation is, you were taking MEG data and trying to classify what speech action someone is doing, or?
No, so the paper discusses about MEG at the start, but then they do go into EEG as a special case. And that's what we have adopted for in this case. So the time snapshot will have all the channels and the time axis, and then sequentially you do spatial and then temporal processing because of that. So the first thing was to get the network from Keras and translate it into NangoDL. And there I explored multiple parameters like what would happen by playing with neuron types, by optimizing the synapse smoothing, just so that we can get more sparse activities and maybe optimize the energy in terms of that. And secondly, as the last point, we wanted to explore the Nango-Lohi platform. So you can see that we start off with something like 49% accuracy at the start of it. The initial smoothing didn't work. For some reason, it needed the firing rate to scale so that it could work. And we can see a pretty much a similar drop of about 5%, 6% when we move on to the Lohi platform directly from there.
Terry, is it possible that you could actually point to stuff while Vivek is talking about it? I'm having a hard time following what he's actually mentioning.
Yeah.
I can't tell what he's referring to.
Sorry. Yes, I will try to do that for these other presentations. Yeah, but these are the accuracy numbers dropping down. And,
yeah. So main neuron types that we explored were the standard ReLU, the spiking ReLU, and the Lohi version of the spiking ReLU. So this was much more of a straightforward study, I would say.
Yep, taking networks and putting them on, existing networks and putting them onto neuromorphic hardware. So, and I'm really happy that the accuracy stays pretty similar. But I do think we want to spend also some time really looking at what ended up happening at the low level in terms of the firing rate. And because that ends up, we've got some interesting methods for estimating energy consumption based on those firing rates. So that might be a nice thing to do next with this. Cool, thank you. All right, Chad, would you like to describe the?
Yeah, sure. Can you hear me?
Yes, I can hear you.
Great. All right. So as an intracortical BCI researcher, I have two kind of interests in spiking neural networks. One was sort of similar to what Vivek was just talking about, and that would be to decode activity where I can actually use the spike timing information instead of just converting it to rates. But in this case, actually what I want to do is build a virtual brain so that I can test my decoders before we actually get to the operating room. And also test for their ability to accommodate changes in the signal non-stationarity, things like that. So I used an online data set from macaque prefrontal cortex, where the monkeys were doing this spatial delayed match to sample task, where they had to look at a fixation point, then a cue would come on, and then it would disappear. Then a little bit later, a sample would come on, and if the sample matched the cue, then it would disappear. And then they would have to respond later by looking to a green target if the sample matched the cue, or to the blue target if the sample did not match the cue. And so I couldn't get a regular spiking neural network to do this task, but pretty easily with the LMU, I was able to do this, thanks to Terry's help, of course. And so in this graph, you can see at the top what the stimulus looks like. So you have the X and Y inputs. And so you can see that for the first two trials, so you have the cue is first and then the sample is immediately after it. And you can see the cue and the sample are not the same. So that would be, that would require the answer to be -1. And then in the next one, they're also not the same. So that would require the answer to be -1. But then in the next trial, they are both the same. So then the answer should be +1. And so here we just have an example of what the spiking looks like. And then on the right is the result of the LMU actually doing this task. And so you have some training data and then sort of train the output layer, and then you have the testing data using new data.
This on the left is the training, on the right is the testing.
Yeah, sorry. And so because I want to use this as a virtual brain to validate our decoders before we actually do the surgery, I want the network to spike as similar to a real data as possible. So the next step was to sort of compare this to real data. Can you, yeah, there we go. So here in the first column, those are just some statistics from the firing rates from the actual monkey data. So coefficient of variation, the firing rates, and the time scales. And then I tried 2 different LMUs. So the first one, the middle column just shows the vanilla MU without anything special done to it. And you can see that the stats are quite different. So then we tried to augment the LMU a little bit. On the left, you can see the changes that we made. So one of them was to set the max firing rates to come from the max firing rates that were found in the neural data. Another is Dale's law, and another is to use heterogeneous synapses, so like the synapse time constants, either come from that distribution or actually the numbers here are from the, the synapse time constants come from that distribution. They're from basically almost 0 to 0.7 seconds. And then also we can play with the LMU's theta knob to try and see if we can get the timescales to approximate the real data. So the numbers, the spiking statistics of the LMU, or of the recurrent neural network in this case, get a little bit closer to what we see in the neural data. I'm still working on some other things, and one of the things that I'm most interested in is figuring out the low dimensional dynamics. While I have the microphone, I just want to say thank you to the Telluride organizers, because I've been interested in spiking neural networks for a while, but never really had a chance to get into them because I didn't really know how to get started. So watching these presentations during the first week and seeing Mango, and then with Terry's help, really made it easy for me to jump in. So even though I'm quite new to this, I have a path forward now. So thank you for that. And I'm done.
Great, thank you. Yeah, I'm very excited about this work. So, yay. Actually, I'm excited about all the work.
Andreas.
So that's,
Awesome.
Go ahead.
Yeah. So, have you made motifs of neurons, or just with inhibitory synapses as well, or how do you really do this, or this is just uniform populations?
For this one, we are actually splitting them up into excitatory and inhibitory populations and imposing Dale's law.
Okay.
And so it's like, this is 80% excitatory, 20% inhibitory.
Okay, well, so this is kind of, because, as you know, I mean, from the work that we did with, that we worked with my student, that doesn't really, it really at the end of the day, that just gets you so far.
Yeah, I think there's definitely a lot more we can do in terms of these motifs, in terms of different ways of structuring the network. But I like that we now have better tools than when Kate was working on this stuff. We've got a lot better about being able to quickly sort of impose different sorts of more biological constraints.
Okay, well, that would be great, because I think that would be, I'm looking at other student here who is interested in taking on that work, and we need to finish a paper, of course, you know.
Ah, yes, good point.
From last year, gee, it's been a year already.
Yep.
What a year.
No,
Anyway,
I will hook up with you after this, and we will.
Yeah, let's
chat
do
about
that.
Cool.
So another question for you, Terry.
Yep.
So when you say that the network emulates PFC spiking, how do I know that you have done this? I mean, all I see are spike rasters and some
to me, mostly it's about these stats that Chad is showing here. Is like, okay, well, what's the coefficient of variation in here? So because that to me is sort of the main measure. I would also be interested in going into a little bit more detail of, do we really want to restructure this and I've been chatting with people, but do we want to restructure things so that it actually respects also the layer structure of the cortex? Because at the moment this is not. This is just arguably maybe going just one layer of doing this excitatory inhibitory populations.
I should say that in most intracortical brain-computer interfaces, we're typically recording from just one layer. The electrodes are usually all 1.5 millimeters deep. We usually don't know what layer that is, though. It's maybe 4, maybe 5, but somewhere in there. Depends on the cortical thickness.
Yep.
Okay. So it's really to just emulate kind of the neural statistics, right? In any layer, any area, I should say. I mean, it's nothing here that we are using yet to emulate the behavior of PFC yet.
Right, yeah, so it's outputting the task, but yes, I mean, what is the behavior of PFC? I don't really have a good way of quantifying that. So one of the next thing that I'm going to be looking at is the lower dimensional dynamics. So basically projecting it into a neural manifold and then looking at the neural trajectories and then seeing if I can get the trajectories to align with the online open source data. One of the problems with the open data is that it wasn't recorded simultaneously, all the different neurons, they were recorded sequentially. So I'm gonna have to go to my own monkey data to do that part. And that makes it a little bit tougher to share. But yeah, that's for me, that's the next step in terms of validating how well does this approximate what's actually going on in the PFC.
Okay, all right, that's great. Thanks.
Thank you.
Cool. Any other questions? All right, let's go on. Oh, there's another slide. There we are. All right, now for something completely different. Let's go connect to Spice. Tanvir, do you want to?
Yeah. Hi, everyone. Hi, Terry. So in this work, we actually demonstrated a proof of concept of Spice and Nengo co-simulation. So what we wanted to do is that, try to write some automated netlist generation scripts that would be helpful to once you have, once you know how your ensemble would look, to have a way so that you can create a fast prototype of your circuit. So we were actually, we accomplished most of the task on building this proof of concept. So on the left-hand figure, you can see from Nengo, a very simple example of approximating y equal x with an ensemble of 50 neurons. And on the right-hand side, you can see that, our scripts that generates, that uses a simple LIF neuron subcircuit, and, it generates all of the circuit components to simulate, and, to verify your work, the system that you're designing in Nengo can actually be translated to a circuit and, help you further along to build, a real demonstration of your design. Yep. So that's about it.
Yep. One of the directions where I'm really interested in that is being able to do things like adjusting the size of different transistors and having that affect the neuron properties, and then being able to use this sort of prototyping in order to say, hey, if I have these sorts of neuron properties, how good am I? How good is the network at approximating this sort of function? That was something that was really important in the braindrop development. And so doing it in a sort of a little bit more generic way here seems really interesting to me.
But this Andreas, I have a couple of nice work. I have a couple questions. The first one, this is when you talk about a linear integrated fire neuron, I mean, at what level are you modeling? I mean, which one? I mean, isn't that the review paper?
It's the one cited down. It's the Chiara Giacomo neuron.
Which is
the
basically a
current
comparator. Are you macro modeling the comparator, or you actually have transistors?
We actually have transistors, and what you can do, it's kind of like, plug and play. You can just change the neuron model, and you can put whatever new subcircuit you want. You just need to make sure, these are the excitation currents, and this would how your input looks like, and you just need to fix your output. That's it.
So, okay, so I don't. What I don't understand is what does Nengo produce?
So, Terry?
Yeah, sure. So the only thing that we're really using Nengo for here is using the built-in tools for doing the find the connection weights that approximates this particular function. So Spice is producing the neural activity. Nengo is providing the mapping from, okay, my input, I've got a single one-dimensional input that's going into this set of 50 neurons. So something has to make it such that each of those neurons gets a different input. And Nengo's generating the connection weights for that.
I see. So it's basically making the weights for the input to the neurons to produce that. And a practical question, okay, that's fair. And a practical question is, which spice are you using? Are you using LT spice or?
We're using NG spice with the
NG.
spice background. Yep.
I
We
see,
are also
okay.
using PySpice. That's a Python tool to connect to with the NG spice library.
Okay, because I think the numerics of this process, I mean, NT spice versus LT spice, which has the same name, are two different engines, and it may be that LT spice is really more appropriate for stiff like this, where you have spiking events.
So the thing is, we actually, so we started both with LT spice and NG spice, and we verified the results are the same for both LT spice and NG spice. One of the reasons we went with NG spice is because a lot of NG spice as a library, it's very easy to integrate. LT spice, not quite so, and that's why like a lot of different products, circuit simulator products actually use NG spice as their background.
What do you mean the library? Can you elaborate? I'm sorry, I have.
No, that's fine. So the thing is, LT spice is kind of like you have to run it as a sub process and send your data to that sub process and get your data back out, and then you need to process this data, right? NG spice actually gives you a .so, so you actually can call it as a library. And
I see.
yeah,
I see.
yes.
Yeah, but
so
then I would be interesting, and I don't know if you have done it, if you have done a scaling comparison where you actually do a factor of 10 number of neurons and see.
Yes. So we actually like for we actually did first with 1 neuron, and then like we scaled it to 50 neuron to see what happens, and can it just produce the similar output that we see in Nengo, and it does. So you can.
Okay, but I mean 15 and 1 is the same,
No, 50.
Oh, 5. Okay, how about 10,000?
That would take a long simulation time. But
okay, well, that's why I'm saying, the numerics of the two systems are very different, and I think at the end of the day, you're going to find that's why people use LT spice for doing switching power supplies, because that is exactly the same stiff problem as neurons. Anyway, we can continue offline. That sounds interesting. Good work.
Great. Thanks, Andreas.
Good tip. Okay, thanks.
Okay, we'll see what else we've got in here. You have Anita or Evelina?
I'm here.
Talk here.
Hello, this is Gianvito. Can you hear me?
Yes, we can hear you.
Okay, hello everyone. So in this branch of the grid project, basically we want to try to explore the possibility to use LMU to
Nope. I've lost audio. Did anyone else lose audio?
We lost his audio. I think you have to fill in.
All right. Sure. If cut in whenever you're there. Right.
yeah. And can you hear me?
Now you're back.
Sorry. I say that basically we want to try to substitute the random generation of the weights for the EPROP network, performing the phoneme classifier with pre-computed weights done with the LMU techniques. This project started into the Telluride, and it started from a curiosity that was raised by Terry during one of the meeting. Can you hear me? Yeah. Okay.
Yep, you're good.
So, and basically we are into the early phase of this project. We don't have so much results to discuss, but I can just tell you about the procedure that we are like to follow. We already started to convert we started from the example that we have about the LMU set for computing for solving the PS MNIST classification. So we are trying to report this network into the Nengo, from the Nengo DL framework to the standard Nengo implementation, so that this will allow us to explore deeply what are the various components of the network, and moreover, it will let us the possibility to substitute the neuron model from rectified linear to a spiking leaf model. So then when we complete this task and we check that the two variants of the task of the PS MNIST classifier are let's say overlapped, and the results are comparable, then we will create we will pass to the second step, that is the second this one, and we will create an NengoDL version of the phoneme recognition for the phoneme classified network, and this will have a similar architecture to the original EPROP TMIT solver. Then when we have this, we can take the weights that we compute with the LMU and put them into the initialization of the network in order to, and then we will check what are the performances of the EPROP version with the LMU initialization. And this is a big interrogative point. We feel that that can let's say be interesting to explore this kind of task, let's say.
Yep.
So
Yeah,
Terry,
so
do you want to add something more?
I would just say that it's a nice merging of the Wolfgang Moss EPROP stuff and the LMU stuff, and hopefully it's the best of both worlds. We'll find out. Anything else? Hey, robots. Lazar, yep.
Yes. Good morning, everyone. Here is morning in California. So what we have here, we have NVIDIA JetBot. The whole idea is to navigate this NVIDIA JetBot using primarily DVS 240 camera. And NVIDIA JetBot has its own RGB camera, and also it has a Jetson Nano small GPU on it, on the platform. But the goal is to use the different control algorithms and compare them on the two different hardware platforms, so Jetson Nano, and we have a Kapua Bay in the Aula lab as well. So Terry, can you move on the next slide? Yeah. So here is the small setup, which I basically did in my living room. So we have JetBot, we have DVS camera, and we have a flashing light, but giving this blinking light, strobe light. So, and that we use this strobe light as a targeted point for our robot. We want to guide our robot to this targeted point. And we want to explore different algorithms. For example, Terry already implemented some of those, and I'm trying to incorporate it, like P controller, PD controller, PID controller. But above everything, we are interested in an adaptive control algorithm. So this is just a static scene, but we want to make this scene more dynamic and to see how actually fast we can adapt to the new environment. On the right side, we can see the DVS reconstructed output, and our detection algorithm detecting the flashing light or our targeted position properly. So we have implemented this in Nengo. The whole idea is having all these algorithms implemented in Nengo and then transfer them on the actual hardware and measure the performance on these two platforms. So performance in terms of energy, but also latency and adaptability. how fast you adapt to the certain task.
Sounds good to me. So I'm looking forward to pushing that farther into the future. Yep.
Mm-hmm.
Yep.
I have a comment. You guys may want to look back a while back. What's his name? He's in Sweden now, not Sweden, Denmark now. One of our regulars had a little collection of robots, each one with an LED and each one with a little DVS camera following each other.
Mm-hmm.
You guys remember the demo?
Yep. Yeah. It's the same light detection algorithm being used here.
Yes.
I see. Okay.
Yep.
But you know, Andreas, you know, is your Conrad who built all that lovely kind of convoy train.
No, this is really much later.
But he was writing all that just in firmware. He was just writing firmware to do that, right? It's fine.
Yeah, running on a basically a little board. You know, I mean, on your board, the board that actually is a little robot. You know, and it has a little
microcontroller. Yeah. That was all.
Here they have a little GPU with a big giant heatsink on it.
Right.
That's true. That's true. Yeah.
Yeah, and we got to find more complicated tasks to make it useful to have all that extra power.
To actually prove that we don't need this heavy part.
Big heatsink, right?
Yeah.
Cool.
Yep. All right, we're getting there. Sorry, we'll see how this all goes.
We were coming to the end. Slowly. So for the next slide, don't expect too much. For Thomas and me, it's a quite new field. We are both first time on Telluride and quite new. Oh, okay. I would give you access, Terry, definitely. But okay, don't worry. What you would see would be the MNIST data set where you see the DVS gesture data set. People are waving hands or making funny movements. And so why did we choose that one? Our idea was to get our hands dirty. We wanted to have dynamic input, event-based input, but also event-based neural networks to compute learning. And we wanted to do it online. So online learning was the point. And first we thought about challenging us with Pong. Then we realized that Pong might be a bit too tough for us as a first shot. I was happy if we scratched the surface. That was nice for me for here. And next year we can dig deeper. But for now, we are really fine as far as we can come. So yeah, here you would have seen some frames of the DVS MNIST data set, but I make them for you. It's something like that. So what the input? The input is we have a DVS camera. It has 128 times 128 pixel, and we fed this output stream as it is directly to LMU units, one hidden layer, 212 of them, and we hoped in a non-supervised, so self-supervised learning, we hoped that it will be able to differentiate between two gestures. So that was what we also, what we wanted to achieve, to recognize one or the other gesture. And it was not working out of the box. And we really tried some initialization, some other values, but in the end, the learning was just not working. It was as it is forgetting what it is doing. Sometimes it got the right reward for detecting the right gesture, but then the next try, it got the same reward for the wrong gesture again. So it was some kind of just randomly choosing something, which doesn't seem to be right. So we thought about maybe the input of 128 times 128 pixels over the whole gesture stream. It is maybe just too much information. It can't be computed effectively. So we introduced a reduction layer, which is taking 4x4 DVS pixels and put them on one neuron. So we reduce the size from 128 times 128 to 32 times 32. And with that reduction, it was not done yet. So the output was still some kind randomly. But if you go on the next slide, as we introduced then time binning, and we fed in the input stream of the gesture in time bins from 100 milliseconds. So all the data is binned in time, and we fed in a long vector of 32 squared for the pixels, and then up to 40 of these time bins together. We fed that in as a vector to the network, and we changed to supervised learning. Then our results increased rapidly to close to 100% accuracy after 1 epoch or 2 epoch of training, which can also be some kind of overfitting already. So we will, there could be a bit more work to do to define now how good it is and how many gestures it can learn. But for us, it was really nice to see. So these results are pretty young. They are coming from 2 hours ago or 3 maybe. So we are pretty happy to make that possible right in time. And
that is the ideal Telluride experience right there. That final rush to get things done before this presentation.
Really, I'm still a bit sweating, but yeah, Terry, if you want to come to the next slide. So that's how the action selection of the output looks like. And as we expected, if we show hand clapping as gesture, the action to vote for hand clapping is the highest, and vice versa for right hand wave. That are the 2 gestures we compared or we used. And then in the end, I would say some personal comments, and I'm not sure about which one to start with. Maybe I start with the cons to have the positive information last. And I hope nobody is getting mad, because it's really not personal and quite open, and I'm really happy to be part of this. But I think we could have done a bit better if we maybe had clarified the project structure from the beginning a bit more. If we had put maybe some constraints about group size or topics, or also maybe data sets to use, because sometimes we run into the problem that data sets are not publicly available. Some have access over the university, but others can't use them, and they can't be shown online. And finally, what I found a bit disappointing was, and that's really nothing you can deal with, it's up to the participants, that 14 people signed in from the project we talked about, or I presented now, but only Thomas and me are active, were active. So all the others just signed in and never post anything, and not even hi, nothing. So that was, for me, felt a bit disappointing, because you are talking in a somehow empty room, which is really unsatisfying. But what I really loved, and that's absolutely honesty, was the first week. I really appreciated. There was so much input for me, to so much new things to learn, and that was really pretty well organized, and I was just happy about participating. And all the ideas about the project was also very great. I really liked them. And Terry, you was always very motivating and great partner to talk, and great leader for us. So at the end, I would say I really enjoyed it, and I'm really happy to be part of that workshop. Thanks for your attention.
Thank you. Glad. Yeah. I think there's a lot of things we can learn for how to do these things better next year, and for these online things. So it's great.
That's how it is if you do things the first time.
We are almost done. I apologize for how long this is going, but I do want to make sure this presentation gets in there. So,
yeah. Hello, can you hear me?
Yep, we can hear you.
Yeah. Hello, everyone. I'm Yuan Zhen from Lehigh University in Pennsylvania. So this is my first Telluride, and during the workshop time period, I'm mainly looking into this digital memory union, just having a closer look at it because it has many good properties I'm very interested in, and some things I don't understand. So I'm doing this with the help of my PhD advisor, Xiaosheng Guo, and also Terry. Thanks for the great help. So first task of this LMU paper is the capacity task. So for this task is to store and recall a sequence that is randomly sampled from the white noise after a certain delay. So the network structure and equations are shown in figure 2, and the results in the paper is shown in figure 1. So one thing I noticed here is that when the delay, which is the t here, and the sequence length increase, the mean square error actually decrease. So this is
Terry, could you point, please?
Oh, sorry.
I can't tell what she's talking. Yeah, thanks.
Yeah. So I think this is at the opposite side of my understanding. Like when the sequence goes longer, it actually does better. So in order to understand this, I'm trying to reproduce the results by their code, and then trying to plot out the input and output of the sequences. So in the figure 3, we can see that the left and right side figure, one of them is so these two figures are the two green dots shown in the figure 1. Yeah, the 2 points. So for the left one is a relatively shorter sequence, and we can see the arrow is relatively larger. The redder one is a longer sequence. The arrow is smaller. So when I'm looking at this figure, actually I'm thinking of one thing, like what is the memory capacity here? Like what we want to define this. I feel like this is the ability to store information with some fixed resources. And then another question comes into my mind, like what is the information in this contiguous input? So my understanding is that it might be the amplitude or frequency or the phase changes of the signal. So therefore, when we're looking at the figure 3 again, so I feel like increasing the sequence length seems increased the sampling position for their results instead of the information length. So this leads me to an experiment which I'm trying to extend this capacity study. That encode a temporal sequence into the amplitude of a sine wave to test the capacity of the LMU. So this capacity really means the ability to store some information we want. So then we go to the next slide. So here we are still using the same network structure as shown in the figure 1. Just to mention, this is ANN. And then the result is shown in the figure 3. So in the left side of this figure, we can see how the information is encoded to this sine wave. So each digit is correspond to the amplitude of the half sine wave. And in the left side example, I'm using 14 hidden layer neurons, and the sequence length is 10. Here, we are trying to output the exactly same sequence after the input sequence are entirely feeding into the network, and the accuracy is 100%. And then I'm trying to extend the sequence length. When the sequence length extended to 1000, and I figured out that we need to increase the hidden layer neuron size to 4,000 in order to get a 100% accuracy. But this encoding scheme turns out to work pretty well. And this can be extended to even longer sequence. But as you noticed, when the sequence length or the digit range increase, we need more hidden layer neurons. This is sort of to enlarge the capacity of this ANN network. So this kind of task is widely used in some memory augmented network work. But for those work, they're using a neural network as a controller and then extended external digital memory, and they are trying the same similar capacity task. But for them, they need to train the network. The advantage of LMU is that we don't need training at all. So the weight matrix, the A, B, WM are just calculated by given the sequence length and the delay as the input. So this is a very good property of this LMU network. But some disadvantages is that one is that we seem to need many hardware resources in order to make this work. And another thing is this is only work for the capacity task. A certain delay reproduce the same sequence now. So for the next step, I'm trying to, so still the previous slides. The next step, so I'm trying to reduce the hardware overhead. And probably looking into the spiking neural network implementation is one of the solutions. Just if you look at the figure 2 here. So if we are consider a spiking neural network implementation of this LMU network, so one good property is that the spiking neural network implementation based on the neural engineering framework just separated the order, which is the Q value, which is the dimension of the state vector of the system, separate that one with the number of neurons in this hidden layer neurons in this network. So we can have a very large Q value, but a very small M value. So I'm trying to check whether that would be a solution, can reduce the hardware overhead, but still have the relatively large memory capacity. Because for a spiking neural network, actually the capacity there is not only the number of hidden layer neurons, because now we have firing patterns and dynamic systems. So the things like firing rate and maybe the complexity of the neuron synapse model will play a role. And then explore different encoding approaches is another thing to do, because this sine wave thing is just some very simple initial start. I think it's not the best way to do it. And we could try to extend it to more tasks like reverse recall or ignore. Yeah, just by changing probably the transfer function, like defining new AMBW matrix. So then we can go to the next slide. So this is another study of LMU. This one is based on the classification task. We have 3 figures here. The left one is the original equation used in the LMU paper. And the middle one is some results I generated when playing with this model. So I just found out that we could reduce some terms in this in the original paper, but get very similar results. In the table, we can see that for the reduced LMU model, we can still get very similar results as the previous one, and in a very few epochs. And this reduction will make the implementation, especially the spiking neural network implementation, a little bit easier. And we can just use 2 recurrent hidden layer, M and H in the middle, to make it work. And just want to point out some advantage of LMU. So this is correspond to the right set figure. So this plot here is one plot shown in the NRU paper published in AAAI 19. So the advantage of LMU, we can see that it's converged really fast, because all the previous algorithms, it needs several epochs to reach a relatively high accuracy. And another thing is LMU is easy to generalize. We can use only 2,000 samples, train 10 epoch, and get larger than 90% testing accuracy for this data set. And this probably due to the orthogonal Legendre polynomial thing. So there are some remaining questions for the classification task. For example, the matrix A and B are designed for the delay task, but why it works so well for the classification task is why I still haven't figured out. And to find out the ability boundary of the LMU, I tried to use the same equation and for the CIFAR10 dataset, which has 32 multivax 3 inputs. And I couldn't get a really good results there. So still need to explore. And another thing, I think maybe using this LMU for TI speech dataset is an interesting thing. So we may not need to do pre-processing that converts the analog inputs to some digital inputs. Like there are some algorithms like model the Cocola model and transfer to digital inputs and then use the relevant model. So probably without LMU, we may not need that process. And this is mentioned by Javato in one of the discussion. And I'm very looking forward to their results. And this is the presentation. And finally, I'll just thank all the organizers of this Telluride workshop. I just feel it's a very good experience for me. I really enjoyed the discussion here, and I also learned many new knowledge here. Yeah, thanks.
Thank you. I think the very last bit we have here, Sakshi, do you want to say a very fast bit about your experience playing with Nengo, and then I think we're done?
Yeah, I can add this. So Telluride was, this was my first time at Telluride, and I was exposed to so many new concepts all at one time. So it was really fun working on the different concepts and also learning new things. Majorly what I did, I did not implement any kind of project or anything. I just played with Nengo. And what I did in it was, I really loved using neurons in Nengo to perform various operations like adding, combining functions, using Nengo to visualize RNNs, learning some basics of semantic pointer architecture. And this was what I did till now. And the future goals maybe would be to implement or integrate Nengo with GANs and higher level cognitive functions. So it was great learning under Terry. Thank you. And it was a great experience at Telluride.
Well, it's
Thanks
good to
a
have
lot.
you. Thank you. And I think we are done. That was longer than I expected, but I had so much fun with all of these different topics, so I hope that was interesting to people.
And I'll present the first part, and then I'll introduce our participants along the way. So the aim of this Learning to Race Challenge was to develop a network or algorithm that learns to drive the car around the racetrack. Here you see the car in very early prototyping. You can see some of the dynamics, the sliding and stuff like that. But using only limited real-time data from trial runs and not allowed to look at the car dynamics model, which is actually buried in the code, but getting perfect state, so no need to do any perception. So that was our goal. It was a kind of a learning, a mixture of machine learning and control. The question is, why do we want to learn this car model? Well, the reason is, my motivation is for NMPC, which stands for Nonlinear Model Predictive Control. And the best way to understand what this offers is to look at this beautiful work on the auto rally built at Georgia Tech from the team of Evangelos Theodorou and James Regg and their students. Auto rally, just remember that. You can find lots of videos on YouTube. You can see one of their real physical cars with all the computation, all the perception, and everything on board, driving around this dirt racetrack at speeds that are competitive with some of the best human drivers. And the way this control actually works is by this so-called NMPC. What they have here, they know kind of the state of the car, and they have a model of the car, a model which is a complex model where they've extracted the parameters by very laborious methods in order so that they can simulate forward in time the consequence of a sequence of control actions. So every one of these little yellow curves here is a slightly varied throttle, acceleration, and braking as they go around these curves. And by doing several thousand of these simulations at every 60th of a second, they can simulate the car's history forward. They can predict the car's history forward in time for several seconds. Then they can just pick the best plan. This is like a brute force, but very effective way to deal with all kinds of things that linear controllers can't do. The problem is you need the car model to do this. And making car models, as I'm going to show you in a moment, is actually very difficult and laborious. So let's look at the car model that we actually use, which is considered a very simple model, but it's hidden from us. And this is a model that we got from the work of Matthias Althoff and with the assistance of Moritz Klischat from TU Munich. They're experts in this car dynamics model. I'll just give you a taste of what this model is because perhaps you're not familiar with it. We're using a very simple so-called single track model where the two rear wheels become one wheel and the two front wheels become one wheel. The car has a certain geometry and mass, and it has a steering angle. Then the force on this front and rear wheel is determined by the longitudinal acceleration only. There's no leaning side to side, by the mass of the car and by the geometry of the car. So, you know, of course, if you accelerate forward, the mass goes to the back and so on. That then gives you the tire loading. From that, you can determine what happens at these tires. And then the whole thing is expressed as a set of these dynamical equations where these X dots are various state variables. There's 7 of them in this particular model. And you can see that the equations here depend on nonlinear functions like sine, cosine, and even nonlinearities where state variables like x4 divides x3. So these are nonlinear dynamical equations, which linear controllers have a hard time dealing with. Moreover, these models have lots and lots of parameters. For example, they have a maximum steering angle, a maximum steering velocity, a maximum velocity, a switching velocity, because actually you switch to a different model at a different speed. There's lots and lots of parameters, maybe like 30 parameters. And they have constraints which linear controllers have a hard time dealing with, like finite steering velocity. You know, when, I don't know if you see me here, but when I turn the steering wheel, it takes me time to turn from one direction to the other. It takes me time for the car to accelerate or stop. This also wreaks havoc with any kind of linear controller. But the question is, given this hidden model, our goal was to see if we could learn this hidden model simply from data. And then once we have that, we could do nonlinear model predictive control with it. Okay, so I hope that's clear. So we started. So we wrote this learning to race platform, got out our joystick controllers like this. I don't know if you see it, and collected data from our simulation. And here is an example of a tri-continental race between India, the US, and Europe at an early stage where you can see these cars are all human controlled. Watch this red car, for instance. Right before it gets to the finish line, it actually does a U-turn instead of crossing it. We were just very, very bad drivers, but every time we drove, we actually did get dynamical systems data. And so we started assembling a team, and this is a picture of the learning to race developers. You know, first I started writing the code. Marcin came along. Antonio wrote the controller. The linear controller he's going to talk about. We were joined also by Nikhil from India, by Ante from University of Zagreb in Croatia, by Mark Harani in Notre Dame, by Krishna Kadami at the University of Maryland, and by Arthur Lobo, who we've never actually seen, but he's located here somewhere. So it's quite an international team of people that were actively pushing code. In fact, code did get pushed. This is to our learning to race repository. This is the commits per day as a function of date. And you can see this acceleration here. There was a lull period, but then it was a rapid acceleration to dozens of commits per day. And here is today on this thing. So you can see the typical kind of panic of actually getting stuff done at the last minute. In the end, we wrote about 5,000 lines of Python from scratch for this project. Now I'm going to pass it over to I think, Antonio. Are you there? Yeah. Can you show yourself? I don't.
Toby, may I first ask a question?
Yeah, sure. By the way, let me show the chat here so that I can see your questions. Oh no, sorry, I didn't want that.
Oh, yeah, I put it also in the chat. You showed from the beginning the real car on the racetrack, right? Which was driving in the rounds. And I saw it also has the idea of driving the curves before it even was there and before it saw the curves. So I was asking myself, was it really learning only the car model, or was it also learning the model of the track? Because,
no, in this first one, I'm driving the car and just simply driving it around, ignoring the track completely. This video here is just to demonstrate.
Right, I don't mean this one. I mean with the real physical car. This one, exactly.
No. This auto rally, this is controlled by the computer. This is controlled all by the computer.
It's calculating the turn before it even knows that the turn will be there. If the track would be non-known, why could it calculate the turn before it is there? You know what I mean?
Oh yeah, it knows the track. It definitely has a map. This one has a map of the track.
And that's a problem, because if you want to go on a new unknown track, it will not work, because you need also not only the model of the car, but also model of the track, and that's
well, like any race car driver, you get better as you drive the track. Yeah, I agree. This is not perfect. You should read about this work.
but you can drive any track, and this one has learned this particular one, and that's the point I want to point on.
It generalizes. If you give it another map of a track, you know, not an oval like this, it can drive it.
That was my question. Okay, great. Okay,
yeah.
good.
It's really beautiful work. I'm not sure how active this work is, but it really inspired me because we have hardware that can accelerate the inference of recurrent neural networks, you know, that we trained on labeled data. And so that was one motivation to see whether we could actually train RNN, and we're going to tell you about that aspect of the project.
Oh yeah, I'm really interested in. Okay, cool.
Okay.
Thanks a lot.
So now let's go on with Antonio, because his job was actually to give us a reference controller. What do we have to beat? So Antonio, you can take over here.
Okay, so if you click, so if we want to develop a controller, we don't have to know the detail about the car dynamics, right? We can just develop a proportional controller. It only controls the steering to aim towards the nearest track waypoint. So if we know the road path, I mean the waypoint list, our actual position, and we know that there is an error, we can implement an algorithm to reduce that error. So we can guess a proportional controller that try to stay in the desired trajectory. So if we can implement a PID controller that is applied to the steering actuator, and we should tune the PID constant that are shown in this equation to get the expected behavior. Okay, so here we can see two examples of the car using the PID controller. In the first one, the car is driving on the easier track. It only drives straight and turn right at its curve. In the second one, the track is more difficult and there are curves in both directions. But we can appreciate that the driving is not very smooth. And we see how the car tries to correct the trajectory frequently. So in this controller, with the controller, we can only go very slow. Try to go fast and it just run off the track or go totally unstable. Then we also borrowed the formula 1/10 the pursuit motion planning algorithm to follow a smooth track trajectory passing through the waypoint. So if we know the waypoint list, the path, we know the car position, and we define the look ahead distance, we can calculate the curvature that the car should follow to reach the next waypoint. Here we can see the geometric interpretation where there is a goal point. Here there is the car, and we have to calculate the radius of the arc, restricting his center to the axis Y. If you click, I can go ahead, Toby. So here we can see the same tracks as before, but in this case, the car is using purpose-fit autopilot. Now we can appreciate that the driving is a bit smoother and faster, but we have a still problem in the sharp curve. So in the second picture, when the car go to this curve, you can see that, okay, we have a steep problem with sharp curve. So, but if you want to do something fancier, you can learn the car model. So now, the driving now is much smoother and we can go faster, but we have some problem. So now, Marcin, I think Marcin is going to introduce the first approach that is trying to model the car dynamics using the RNNs.
Thanks, Antonio.
Okay.
So over last weeks, together with Arthur, Mark, and Nikhil, we tried to answer the question, is RNN, the recurrent neural network, is it the right tool to model such car dynamics? Our general idea was to take an RNN network to feed in, on the one hand side, the control command, that may be throttle, brake, steering. On the other hand side, the state of the car, that is position, velocity, some subset of state of the car, and try to predict with RNN the future state of the car. In fact, during our work, we tried two approaches. One of these approaches is one-to-one approach. And this approach, each input of command plus state results in a prediction of a state at the next time step. That means we take one time step and information about one time step and wants to predict the next time step. Also, Arthur, which was our great and involved but never visible or reachable contributor, did a sequence-to-sequence approach. In this approach, a sequence of states predicts a sequence of commands, and he was very successful with it. It results in our first successful control of control with RNN. And in fact, here you see a car being driven by an RNN controller. It is not perfect, but it's working very nice. Good. Before I give the floor to Mark to show you the first, so this would be a slide of Arthur, but I guess
do we have Arthur with us? Is there Arthur here? I don't think so, right? No, no Arthur. Okay.
Okay.
So we'll go on.
So this is the
We skip this then. This is the RNN.
It's the general architecture Arthur was using, but then if Arthur, you see it's 4 input 3 output LSTM encoder decoder, but as he is not here, we'll just leave it. Maybe you can read it later or try to contact him.
Okay.
Before I will give the floor to Mark to show the first results we achieved with our one-to-one approach, I would like to say a few words about the tool we developed for RNN training. I think it is worth it because we developed a bunch of scripts which allow to train networks in a very flexible way. You can just specify by a string the architecture of network you want to train. The same, you can give a list of inputs and outputs you want to be picked from your data set. You can specify the files you want to use for training. We also have an interface to the L2Race simulator, which can be also used as an interface for some real-time application. And last but not least, we prepared some visualization tools with Matplotlib and TensorBoard. And so I think it is a very nice byproduct of this L2Race challenge that we did a general tool which hopefully can help also other people to quickly make a first assessment if RNN is something useful for their data, to model their data or not. Okay, so now I would ask Mark to present our first result we achieved with one-to-one approach.
So our first experiment is what we like to call the open loop experiment, where we give the neural network the full state information, full simulation information, both the state and commands. And to knock on Simone's point earlier, we do train on different tracks and we test on the oval track. So the goal for us is just to capture the underlying dynamics of the car in this first test. And you see that we're able to capture the position very well. You can see that we start at the green dot, end at the red dot, and that the blue line is the prediction line, and you can't even see the dotted dashed black line, which is the prediction line. And they are just right on top of each other. The next plot shows the actual body angle of the car, which we wanted to look at because it goes between -180 and 180, which makes it discontinuous. And you have these big jumps, whether or not it is at -180 or 179. So it was able to match that perfectly. And then finally, we were looking at just the speed because we do a lot of braking, slowing up or slowing down and speeding up, like speeding up at straightaways and slowing down and braking when we need to turn. And so our next experiment is the closed loop experiment. Can you also have the next little graphic? Okay, where we do what's called the closed loop experiment, where after a certain time, we rely only on our model for the state information. So it only has to learn from the control, or it only has to predict from the controller actions. So now with imperfect state data, you could see that this is less than ideal. So after the orange dot, it has the internal memory model from the RNN to do the rest of the prediction. So it starts off pretty well for like the first few time steps, but after a couple time steps, it just diverges and goes, it takes the first turn too hard and isn't able to keep the position. But it still generally looks like it's doing an oval. The next plot shows that the body angle, even though that it doesn't match, it still has some sort of periodic function, which is good because the underlying model is composed of sine and cosine layers. So even though it's not able to exactly predict it, it's able to predict a function that is similar to it. And finally, if you look at velocity, you could see that the ridges kind of look similar. If you squint your eyes, there's little ridges of us braking and going forward and going slowly, or speeding up and slowing down. But the overall magnitude of how fast the car is going is not something that the network that we used was able to predict. So to sum up, we can follow the trends of the data, but we aren't really good at the details in the closed loop environment yet. So we're going next.
Yeah.
So next I'll hand it off to Krishna to talk about our next approach for L2 race, Sydney.
Hi guys. So this is the second method we have tried, which is called SINDI. It stands for Sparse Identification of Nonlinear Dynamics. It's by I'll talk about this like basic with an example, and I'll walk you through it. What does it mean? So basically this figure has been taken from this paper mentioned below. So there is a dynamical system which is given by this expression. So the goal is like to predict the right side of these expressions with like given data X, Y, and Z. So I have some data, but I need to predict what kind of format is like the right-hand side expression is. So in order for that, like I need 3 steps. Like the first is like I need the data X, Y, Z sampled at different times. And the second is like we have to construct a library theta of X consisting of like candidate nonlinear functions. So basically each column represents a candidate function. It can be a linear, it can be a constant, it can be a polynomial, or it can be its trigonometric sine, cosine, trig, or anything. So, and then finally we have to predict a sparse coefficients that fit the data well using regression methods. So the only assumption in this here is like most physical systems have only like few terms that define the dynamics, making the governing equation sparse. That's the assumption in SINDI. So, and this is the model that is the SINDI has generated, which is like in the right side model output, like if you, yeah, in the green box. And then this figure shows the output that SINDI has generated. It looks very similar to the original model, but our question was like, will it be able to predict the car dynamics? The answer is yes. So this is the SINDI trained on a PID controller car data. As like Antonio pointed out, we have used 2 types of controllers. One is PID, the other is pure pursuit. But we were like, how well does SINDI actually predict the model? That was the question. So the GIF shows you the PID, like the red car is like the true simulated model. And the silver one here is like running the ghost car, it's running the SINDI model. So initially it tries to catch up to the true model, but eventually it fails, like after a point it tries to diverge. Similarly that you have seen in the RNN case. The next plot, Toby, can you take me? Yeah, this is like the position X, position Y, velocity X, velocity Y, and the body angle with respect to time. So the black line indicates the true data and the red line indicates the Cindy model. Again, like it tries to catch up in the beginning, but again, the Cindy model tries to deviate, but it, as I said earlier, it follows the same trend. So then we were like, can we make it any better? So then we decided, okay, let's do a pure pursuit, like let's feed in Cindy, like the pure pursuit controller data. So this is how it looks. Again, the red car is the true model and the silver one is the ghost car, which is like running the Cindy model. Here, it follows the same trend, but like it's in the GIF, you see like it's deviating, but the trend is followed. So it's way better than the PID controller. And if you look at the positional, like the graph, next graph too. So again, this is the position X, position Y, velocity X, velocity Y, and the body angle with respect to time. So the red is the Cindy model and the black one is the true data. So this method predicts the model well when compared to the PID method. So that's the big thing, like you need a good data for Cindy to like generate a good model. And it's a promising approach, as I said, that requires good data and results in a cheap model, but we just scratched the surface to say.
Okay, thank you, Krishna. So that's it. That's what we got done. We made a real-time Python multiplayer internet car racing game. We established an enthusiastic intercontinental team. We implemented classic linear car controllers, saw that they can only go very slow. We started to learn car dynamics from data using 3 different methods. We had a lot of fun, and we're beginners, it's obvious, but now we went through kindergarten, which is cool. Now it's time for a live demo. So stand by, hold your breath, because we're now going to demonstrate or attempt to demonstrate for you a live intercontinental race of humans versus machines. And just to introduce this, I noticed on the Slack channel of L2 Race, there was a furious chat among Marcin, Krishna, Antonio, and I guess others. And Antonio asked, the question is, do we want the machine to win or do something balanced? Version 2 with proper values, I think the machine always win. So now we're going to see if that's true. Now, my job here is to start the simulation program in spectator mode. So we're all talking to the remote computer, which is at a company here in Switzerland. And we're all speaking to this server with UDP packets at a furious rate, just like you're hearing me with UDP packets sent over the network. And people from different parts of the world here, Spain, Switzerland, and Croatia, have now started cars on this racetrack. Are you guys there? You guys should show your video too, if possible, so we can see you. We see here Marcin, Krishna, Ante, and Nikhil, 4 cars running on the race. And one of these cars is going to be controlled, or maybe 2 of them, is going to be controlled by the pure pursuit controller. Are you guys there? I don't know which one is which here.
Krishna is pure pursuit.
Pure pursuit, which I can't tell. We didn't do a good job labeling it. But one of these cars, we'll find out later which one it is. You guys should say, is controlled by the pure pursuit. The others are controlled by humans. Okay, everybody reset yourself back to the starting line. And on your marks, get set, go. This is a 1-lap race in the interest of time. We see the humans, Ante and Marcin, are well in the lead, but they're almost hitting the yellow sand on the edge of the road where they slow down by a factor of 5 or 6. It looks like Krishna is lagging way behind. Ante is about to go around and, the human won the race. But he went off the track. Oh no, Marcin went into the sand and now he's slowed down to an incredibly slow rate trying to dig his way out of the sand. And he's battling it out with Krishna's pure pursuit controller, which is steadily following and faithfully following the waypoints. Yes, but the humans still won the race. Okay. All right, congratulations guys, bravo. Okay, so from us, I think that's it, unless there are questions. I would ask all the team members here to get on the screen if you're there, turn on your video. And I'm gonna shoot a video right now with us. Antonio, okay, so you ready? Okay, I think I'm already shooting it, but I'll take another shot. Oh, hey, Terry. It's really great you're there. One more shot.
Great demo.
Yeah, thanks. So, we're clearly beginners, but that's where we got to at this point. And so I'm really happy. I don't know if you guys have any words.
I had one question. Did you guys look at feedback linearization or those types of techniques?
No, none of that stuff, man. We're not control people. We're beginners.
Yeah, well,
we were trying to get somebody who knows something about control involved, but nobody got involved. So yeah, but we want to learn. We want to join. Our big goal is to join, efficient machine learning with control. But this is really just a starting point, and with hardware inference. Right? So that's our goal, ultimately. Cool. Okay. Thanks a lot, everybody.
So this is about our final challenge, the metal challenge. This is going to be a little bit shorter than the other challenges. What I'm going to do is just give you a quick overview of what we wanted to do here. So the main motivation of meta learning in the neuromorphic engineering world, I think, comes from the idea that we can do a lot of computation offline on computers without worrying about power or resources. And so that fits really well with the idea that we can pre-train or meta-train offline. And then in order to apply our model to the real world, well, we can just do small adaptations on site. Or for example, on neuromorphic hardware. And this is some work that we did with my student, Kenneth Stewart. So we're basically training offline on a GPU and then just training a couple of the last layers on the neuromorphic hardware using some of the techniques that we've been working on a while with synaptic plasticity and the surrogate gradient methods. So this is, I think, one of the main motivations why we should think of meta learning or few-shot learning as an application in the field of neuromorphic engineering. And so this challenge basically had two aspects to it. So one was, well, can we come up with a data set that we can use for meta learning? These meta learning data sets often are a little bit on the opposite of our traditional data sets where we have a lot of instances per classes. Instead, what we want is a lot of classes and few instances, right? So this way we can basically do this idea of few-shot learning, that we can see new things and adapt to those new things and thus evaluate our meta learning approaches. So that was the first approach. And the second approach is, of course, once we have these meta learning data sets or data sets that can be used for meta learning, so we're going to explore some different approaches, apply them on classical neural networks as well as spiking neural networks. Okay. So the main setup here really follows this idea of few-shot learning. Okay, so this is, I think, going to come up for the following few slides later. It's basically that you have multiple data sets. So every training step in meta learning consists of training and testing. So here's how it works. So you start with one data set that basically the first task may be to distinguish between cats and birds, right? And so your network may learn to do this. And then you teach it another task, which might be to classify between flowers and bikes. And then you show a new data set, which is, for example, distinguishing between dog and otter, but very few instances of dogs and otters. Well, in this case, in this figure, it has the same number of instances, but try to imagine that we just have one instance of a dog and one instance of an otter, and we would like to classify one or the other. The goal is to do well at this testing stage, just with a few samples here. And this is possible if you've learned a good model in the first stage, a good model of these tasks. Okay. So one of the data sets that we came up with was basically following an idea that was already proposed in the meta learning field, which was this double MNIST task. So you can basically combine these digits in a single frame. And so instead of having just 10 classes, you have 100 classes. So the goal here was just, the first step was just to take those this idea and apply it to the neuromorphic MNIST that Garrick Orchard and colleagues put together, and basically build a time-dependent version of this double MNIST task with event trains. And this was implemented, actually went through a lot of trouble to implement this as part of an existing
PyTorch meta learning library, which basically builds this NMNIST dataset and organizes this task sampling by basically sampling, you know, a small data set of 5 different classes, each of them consisting of the 5 of the 100 possibilities we have in double MNIST. And so once we have this, basically we can generate these batches in parallel and thus really improve the speed of meta learning and basically use all the other standard optimization-based meta learning techniques that are out there. And one of the meta learning techniques, optimization-based meta learning techniques that's out there is called model agnostic meta learning. And the really nice thing about this approach is that it's model agnostic. So if we can plug in a classical neural network, we should also be able to plug in a spiking neural network, such as we've been training so far in the past. And the way that this works is basically that you find an initialization to the parameters here. Let's imagine this is the initialization such that it only takes one or few steps to reach these points here indicated by the theta stars. These are thetas are the parameters, and those theta stars would be good solutions to, for example, task 1, task 2, and task 3. So the real goal is to find this point here. And the way that this works is, I mean, don't be distracted too much about the details of this pseudo algorithm here, but I think it's still interesting to show it. Basically, the way that this works is that you sample different tasks. This may mean, for example, what was it, the dog versus the cat, or the bird versus whatever. And you basically compute one update step there on the parameters. And once you have all these theta primes, which are now the new parameters that are each of them adapted to this new task, then at the end of this loop, you update the weights, but not with respect to the new parameters, but rather with respect to the old parameters. You basically take a derivative of this update itself with respect to the parameters. So this is like the derivative of the derivative, and it's really, it fits well to this idea that meta learning is basically learning to learn. So it's the gradient of a gradient. And so this means that your network has to be 2 times differentiable. So you need to be able to calculate Hessians there. There are also versions of the same algorithm that doesn't need the second derivative, but that works slightly not as well, but still good enough that we can it's usable. So we applied this on the double NMNIST task, and not too surprisingly, so on the standard convolutional neural network, so there's no time component here, there's no spiking component, but just really using these events. And so, and because we don't have time, we basically just flattened the image by counting the spikes. So this is what the data now looks like. And so this worked really well with this mammal, and first order mammal is that same version without the gradients. This is a sample, a result that was taken from the website of those who did this double MNIST, and this mammal method works much better. I think partly it's because the implementation of the mammal, which was just taken on implementation that already existed, was a better made model. Rather than being a difference in the data sets. So this was our first success story. So this worked pretty well. Now the second step here was to apply this idea of surrogate learning, surrogate gradient learning. Basically, we can smooth some of the learning dynamics in spiking neural networks, and which is expressed as a recurrent neural network. And basically approximates the gradients using these smooth functions. So this is a long story. I won't go back to this, but if you're interested, I mean, this is some things that I talked about in the tutorial. And so it's fairly easy just to take this network, the same convolutional network, just expand it in time with the spiking dynamics and to plug it into mammal. That unfortunately did not work, so I don't have any results here. So it's the accuracy did not budge from chance level, so that's still where we're stuck now. But the nice and one of the reasons possible reasons here is that, I mean, we have also this time dependence as well as the necessity for second order derivatives. So that's something that we can't do. The surrogate gradient approach we haven't yet tried this with Hessians. And so that might be one reason. And just because, I mean, there's a lot of parameters also to tune for mammals, so it might just mean that we need more time to figure those out. But on the plus, I'm really happy with this result because it turns out that this training, this mammal learning is actually tractable time-wise. So it does fit on a single GPU. It takes 1 week instead of 1 day, but we can do it. And I think that's, if it's just a matter of finding those hyperparameters, I think we're on a really good track there. Right, so this is some work that we did together in the group, and I think in the next slides we're going to have Clemens actually present his project. Clemens, are you online?
I'm online.
Okay,
yeah.
great. So I'll try to point on the figures as you talk and move on slides.
Okay, very good. Yeah. So I was trying to take inspiration from traditional machine learning, how they done the few-shot learning, and there was like one paper at Europe 2019. Which was called like charting the right manifold mixing with few-shot learning. I was just taking very few ideas from that, and I want to apply that to spiking neural networks. So their basic idea is to say we have a training phase and we have a fine-tuning phase. During the training phase, they basically take all the base data with the many examples and many classes and try to train a classifier. And this backbone they're training there basically remains fixed and is then fine-tuned with like an additional classifier to actually classify new data. So we have those two phases, and one of their ideas was to say, in order to train a very good backbone, they are saying, well, one, we have like our base classes, we do that classification, and we're having some kind of auxiliary loss. The auxiliary loss there basically serves as another task to basically get the backbone to generalize better and like also be better for new unseen classes. We tried to implement it. For the auxiliary loss, we took a self-supervised task, so we didn't need any extra data. We were just rotating pictures. So we were rotating them by 90 degrees, 180, 270s. So the auxiliary classifier had to predict how often did we rotate the picture. And the normal classifier just had to say like, what kind of class are we seeing here? We can go on one more slide. And we were trying to do that with a spiking neural network. We took some inspiration from Découlé there in terms of the architecture. It was a convolutional neural network. So with our input on the double MNIST downsample to 32 by 32, and then it goes through a convolutional max pooling, convolutional max pooling layer. And then we have like this kind of output vector, this feature vector you can see there, this 1 by 1600. And this feature vector is essentially what goes into our classifier. There we basically train our backbone, and then we train the classifier, and the fine tuning we say, let's take a new classifier, take the backbone as we have it trained on the big data set and train it again. I was trying that, and we can see in the next slide next slide, please. Thank you. That I didn't get that far, but I think we could show that basically the basic idea makes some sense. So the training for the backbone took me a long time, and we can see how I was training on 20 classes, and my accuracy in the accuracy graph here didn't go up that much. So like my backbone training wasn't that successful. I had to play with a lot of hyperparameters. I'm still playing on that, but my best, what I got so far was like 20%. And then taking this backbone and basically plugging it into our testing, we can see that we achieved better accuracies than just taking a non-pre-trained backbone plus a classifier. I think that was like my promising approach there, that like on the 5-way 5-shot, I showed that basically the baseline is taking a completely untrained network, backbone plus classifier, backbone was untrained, and we got like 24%. But if we take our pre-trained backbone from our, 20% accurate backbone, we actually are better than our baseline. This is also on the double MNIST. I was happy to see that. I'm still working on like training the hyperparameters, which are really important for the networks to actually learn something. And I hope to actually push that further up and get it somewhere close to the normal percentage we would like to see there. So it's the further work is basically train the classifier and the backbone better, maybe add some additional loss functions in there, which the Neurops paper did, and then maybe actually roll it out on data sets which are even more spatial temporal. So like we could think about a DVS gesture, double DVS gesture, where we actually have like temporal and spatial information, which is very meaningful there, and train it on that. Yeah, that's so far from our side.
Okay, thanks, Clemens. We may have Sumit online, or maybe not. It's past midnight in Singapore where Sumit is, so let's see if he's around.
That's a tough talk to give, man. Can you present it, Emre?
He is online.
Yeah, I see him online actually. Yeah.
Yeah, he is
Oh.
here.
Sumit has a picture of
I
Andreas.
see Sumit. Oh yeah, it's the same Sumit I know. Right, from Telluride
Yeah,
last year.
that's right. That's right.
Yeah.
Sumit, are you there?
We don't hear you. We don't see you. We don't hear you.
How about now?
Yeah.
Now we hear you and see you. Good.
Okay, cool. Yeah. So good to see everyone. So on this meta learning challenge, the idea that we looked at was we have this American Sign Language DVS just classification task that's already there, and what we wanted to see was, can we really translate a network that is trained on some other neuromorphic data set, and can you get good future learning accuracies on that? And for this, we had two different candidates. One is the IBM DVS classification. That's I guess it's quite popular. The other one that we looked at was this hand gesture classification. A portion of this was we worked on it in last year's Telluride. So this was a part of sensor fusion work, but what I wanted to do was I wanted to leverage the trained network and see if we could do future learning on DVS American Sign Language classes. So that has basically 24 classes, recording of 100 milliseconds with the Davis camera. Can you go next slide, please? Next slide, yeah. So the first one we tried it with the DVS gesture. So this is the same network that we demonstrated with Garrick last year. So it's the same network, but we just cut off the last layer and we try and just train the last fully connected layer to the 24 American Sign Language classes. And with just one look at the data set, we get around 54%. That's compared to the baseline of like 4% or something. It's pretty good, but we still think that we could do better. One of the reasons why we think that it doesn't do better is because in ASL, as we saw in the previous slide, it's a big image of hand, and the DVS just features don't really translate to something like that, because here in DVS we see a full image. So that's why we looked into the hand gesture data set, because it's more similar. So you get, we hope to get a more better feature extraction along the way. Next slide, please, Emre. Yeah. So then we did the same kind of approach with hand gesture training. So this was part of the sensor fusion work that we did last year. So this is also CNN. So we just took the convolution part of the network because the input frames were slightly different, but the convolution part is able to handle it, and we just connected a fully connected layer on top of it. We just discarded the previous fully connected layers and added a new fully connected layers and trained it. And it seems that we with a couple of look at the data, we can get pretty much 78% accuracy. I think that's quite good for just 10 epoch. So
Can you, what is epoch here? What does epoch mean?
Epoch is one look at the data, the training data. So there are, I believe, a couple of hundred samples per class.
Are you using LSTM on this? What are this is just
these are spiking CNNs.
This is just plain non.
Yes, feed forwards.
Yeah, well, you're not gonna. I mean, unless you go to LSTMs, we've done gait recognition, which is and you get like 99%. You go from something like this to 99% once you start doing dynamic.
I don't think so, Andres. I don't think that's the problem here. I mean, we've been using these things for hand gestures. Sorry, go on.
Okay, well, you're in the 70s.
Yeah, but we're just looking at training it just on few sorts, right? So we could train it for like thousands of folks, and I believe the accuracy will go up.
This is great work. I'm just pointing out that unless we can compete with the people that do it,
your reference is wrong.
Get 100% on this, then we're not competitive.
No, Andres, your reference is wrong. You should not refer. Your baseline is wrong. I mean, this is not comparing to what you can do with an LSTM with the entire data set. We're looking at what you can do with a couple of samples. If you do this, even with your LSTMs and other hardware, and so non-spiking, then you'll get the same numbers, or maybe something related. Probably even worse.
It's great. Yeah. I think this is really great work, guys. I mean, I'm just being a local guy that normally would be sitting in the back of the room and complaining.
I know, but here we're just looking at few sort of the samples.
No, great work. That's great. Yeah.
I mean, without meta training, few shot, you basically get no accuracy, right? I mean, you really need to do this.
Well, that's a problem.
And that's but this is what the real world is. The real world isn't you get 1,000 samples of every gesture. You just get one, and can you adapt to that? And this is a real problem in deep learning. That's the main step. Often when you go to the deep learning models to the real world, you need, and the data sets don't match. They need to adapt, and this is really I think.
I get it.
Direction in that.
Great.
And I'm sorry, Emre and Sumit. So to be clear, there is context, right? There should be a temporal context here, right? It's not purely a instantaneous feed-forward network. There is a context of history here, right? Correct?
There is a short temporal context.
Exactly.
You don't have like a long temporal sequence.
Yes.
Like in
so it's like FIR versus IIR,
yes,
right?
Yes,
that's true.
Thanks.
Yeah, but these particular gestures are just symbols. They should be rather called not gestures. They should be called hand symbols. They don't have dynamics like it doesn't matter if you're moving up, down, left, right. It's really, these are just hand symbols, not gestures.
Well, and that's a
which
problem.
is fine, right? You can use a CNN for that, no problem.
I mean, unless you put dynamics.
I agree with that.
Yeah. It's not really ASL. ASL is really dynamic, right?
Yes.
Yes, I mean, you really should. Yeah. It's okay, Andreas. It's what can they do in a short time?
Yeah.
Good start.
All right, so that's I think that's it. There's that's the end of our side. So we had a small group, but this is some exciting project came out of this. So thanks a lot for the presentation, guys, and thanks a lot for listening.
Yeah, and we're almost done now with everything except we have a couple of important announcements to your benefit, potential benefit. First of all, I want to remind everybody that there is this 2020 Misha Mahal Prize to the tune of, this is starting to get significant money. $10,000 is the prize, and to get this prize, the submission deadline is 31st of October 2020. It's 7 weeks from now. It's open to any individual or research group worldwide by direct application or by nomination. If you think somebody else deserves it, you can nominate them, but that means you have to write a good application for them. It has to be any real, demonstrable, innovative hardware, software, or algorithm. It's just 4 A4 pages, English description of the work, its novelty, potential impact, and performance. You have to include images and data and links to relevant supporting documents, papers, videos, etc. And resubmission of revised applications are encouraged. You can submit multiple times. Submit your hyperlink PDF to this prize at mahalprize.org. And if you have any questions, then contact anyforum.ch. So join me with Misha to submit your project for 2020. And for the sake of the jury, I don't know if Terry is there, The jury wants creativity, not seniority, and evidence, not promises, plus keep it short and sweet. Okay.
Yeah.
So
and,
finally, yeah.
You know, so, you know, judging previous applications, one of the problems we had was that there wasn't, the references weren't there to, you know, document that we could go back and see if what was built. And so, you know, we only ask for a few pages, but the references are very important.
Yeah. Peer review. Evidence. Okay. Okay, good. Thanks a lot. Anything else? Any other questions about that? Okay, so the very last slide, last word for official closing of the workshop. I don't know, maybe some of the other organizers have something to say here. First of all, big thanks to everybody, all the organizers, especially all the participants, and very especially all the challenge participants and the speakers who presented all the beautiful talks in the first week. The workshop is actually funded for the next 5 years by the National Science Foundation of the USA. We're considering a dual online plus physical event for 2021. So part of the next year's workshop, if we can do a physical workshop, it's not at all clear. We may make some of the sessions actually dual online. And I think that'd be really useful for people that either don't get admitted or just, you know, can't make it to the workshop for some other reason.
It's called hybrid.
What was that, Andreas?
It's called hybrid.
Hybrid, yeah, hybrid. Okay, hybrid, okay. And project work from this year will continue. Look out for publications from these 2020 challenges. Take some time for that. The Slack workspace space will stay up to continue allowing work on the projects. And please help us plan for next year by filling out our survey. I believe I'm going to paste now onto the chat of the, if I can get to it. I'm having a terrible time getting this chat. Yeah, here it is. I'm going to paste onto the chat direct link to the survey. In fact, a direct link, I believe, to the slides. I think this is the slide. If you go to that, you'll come to this link. Fill out this survey and it'll give us valuable feedback about the workshop. We'll also circulate it on Slack. And very, very last thing, see you in 2021. And do you know what this is here? Stick around for the after party. Go to this GatherTown link, join us in Terry Stewart's Telluride GatherTown. And if you want to play some poker, meet at the Sheridan Bar in this poker room link. So we can be on GatherTown, all grouped together at Sheridan Bar, which I think is over here somewhere. And I'll just go straight to this link right now to show you how that works. I don't know if you guys did. My name is Toby, yes. And I'm there, right? That's me. I can turn on my camera here. Terry, please give more hints if you, oh, my camera is being used by Zoom, so I can't do it right now. Okay, there, Terry is next to me. And as soon as I release the camera from Zoom, I'll be in this GatherTown space. So come on, everybody who wants to, no cost, no obligation, come and join and hang out and we can chatter with each other. I leave the floor open now for any comments and a group photo of everybody who stuck around, all 48 of us who stuck around to the end. Suchi, are you still there? Okay, good.
Everyone turn on their
usually we get usually about half the people that manage to turn on their camera. And once you go over to GatherTown, Terry will give you a nice little tutorial how to run this thing. It takes literally like 60 seconds to learn.
Tell me what is the link?
The link is in the presentation slides, which I just put on the chat of Zoom, and I will also put it onto, just look in the chat of Zoom.
Okay. I also put a link to the GatherTown in the chat here.
Okay.
I'll post it in the Slack
as
as
well.
well.
My sister is here from Pasadena. Hi, Ladina. Okay, we're still, Ashley is there, Dimitri, yeah. Various other people are there, but they haven't managed to turn on their camera. Vivek, are you still there? Alpha? Okay, I don't know if everybody has camera. Okay, ready? I'm gonna take a picture. One, wait a sec. What happened to you? Okay, Sakshi, okay, ready? Gabrielle, aim your camera down, man. All we see is your chin.
Cornelia.
It doesn't
Cornelia,
work.
where are you?
Okay, okay. Because GatherTown takes my camera. Okay.
Yeah, GatherTown is stealing your camera. You have to switch it off. Antonio is there. Sumit, are you still up? Man, it's now 1 a.m. almost. You can stay up for this. Okay, and Checho, I think we lost her. Okay, anyway, that's really great. I think some other people are off screen. Ready? 1, 2, 3.
Cheese.
Bravo. Should I take one more? Ready? On the count of 3. 3, 2, 1. Okay, good.
Cheese.
Very good. I'm going to now share this this photo on, I guess, on the announcements of the Slack. So look out for it there. Okay, see you over in the town. Bring your tequila.